Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Today's part for 4 parts of QbD with the theme of discussion is From Development to Commercial Control. This part outlines a sophisticated framework for bioprocessing lifecycle management by integrating quality by design (QbD) principles with advanced digital tools. It details how a robust control strategy links process parameters to product quality through real-time monitoring and hybrid feedback mechanisms. The sources describe a multi-stage validation lifecycle that transitions from initial design to continuous commercial verification and knowledge management. Furthermore, the discussion explores the complexities of continuous bioprocessing and how artificial intelligence, machine learning, and digital twins enhance process predictability. Ultimately, these elements combine to transform biomanufacturing into a dynamic, data-driven system capable of constant improvement and regulatory compliance.
Welcome to the debate. Today, we are leaving the classroom behind. We've spent our previous discussions meticulously designing the car, defining the chassis, the engine specs, the aerodynamics, all using the framework of quality by design. But today we are taking that car out on the highway. We're talking about Lesson 4, control strategy, life cycle, and the, let's say, controversial role of AI in bioprocessing.
That's right. And if I can extend that metaphor a little bit, you want to take this car out on the highway, set it to autopilot, and what? Take a nap? I, on the other hand, want to keep my hands firmly on the wheel. Today is really about the transition from a theoretical design on paper to the messy, high-stakes, chaotic reality of the manufacturing floor.
And the central question we are wrestling with is this: does the future of biopharma lie in dynamic, AI-driven control strategies that proactively manage variability? Or, and this is the core of it, does the sheer complexity of these black box systems introduce operational risks that outweigh the benefits of our established, robust frameworks?
It's the classic tension between optimization and robustness. You're representing the future-ready view, the idea that we can algorithmically predict our way out of trouble.
I wouldn't say predict our way out of trouble, but I do believe that QbD, quality by design, only achieves its full promise when it stops being a static document and becomes a dynamic operating system. We need feed-forward controls, real-time release testing, and yes, AI to make sense of it all.
And I'm taking the robustness and reality view. I've seen too many fancy control loops crash a batch that a simple manual operator or a basic PID loop would have saved. I'm skeptical of unproven sensors, the nightmare of validating continuous flow, and the governance gap around digital twins. Reliability has to come first.
Fair enough. Let's get into the position statements. I'll kick us off. For decades, this industry has treated the control strategy as a compliance exercise. You define your set points, you hand the dossier to the regulator, and you pretty much freeze the process in ember. But biology isn't static. Raw materials drift, columns degrade. My position is that the control strategy must be the active link between the process and the patient. It's not enough to just have a design space. We need to move from feedback control, which is always reacting to the past, to feed-forward control, which anticipates the future. The ultimate goal is real-time release testing, or RTRT. We need to stop testing quality into the product after it's made and start controlling quality during the process using process analytical technology, or PAT.
Okay, I hear you. And strictly on a PowerPoint slide, that looks fantastic. But here is my reality. Complexity is the enemy of reliability. You talk about feed-forward control as a solution. I see it as an amplifier of risk. Feed-forward relies on a model. It predicts, hey, a disturbance is coming, let's change the process. If that model is wrong, even by a little bit, you aren't fixing a problem, you are actively creating one. You're introducing a deviation based on, well, a model's hallucination. I also worry about the reliance on soft sensors, using math to guess at variables like biomass or product concentration. If those sensors drift, your entire strategy just collapses. Give me a robust PID loop that reacts to reality, not a model that guesses at the future.
Guesses is a strong word, but I see where you're coming from. Let's dig into that specific point, though. The battle between feedback and feed-forward control. You're defending the traditional feedback loop, but we have to look at the biology. Fermentation is incredibly fast. Cells change their metabolic state in minutes.
And a PID loop can react in milliseconds.
The controller can, sure, but the physics can't. Let's take the example of oxygen limitation from the lesson material. In your preferred feedback world, you wait for the dissolved oxygen sensor to drop. Then the controller sees the error. Then it ramps up the impeller speed. Then the oxygen physically has to transfer into the liquid. By the time the oxygen actually hits the cell has been starving for 5 minutes. It has already shifted its metabolism. It's already making impurities. You reacted too late.
And your solution?
Feed-forward logic. We know we are about to add a bolus of glucose feed. Our metabolic model knows this will spike oxygen demand. So the system ramps the aeration before the feed hits the tank. We preempt the starvation. We break the causal chain before it ever impacts the critical quality attributes.
That's a compelling narrative, but let's talk about the actuator limit. You start ramping aeration early based on a model prediction. But what if the feed pump has a momentary clog? The feed, it doesn't go in. Now you've ramped up the impeller. You are shearing the cells with high agitation, prepping for a feast that never arrived. You have just stressed the cells and created an impurity profile that wouldn't have existed if you had just waited for the sensor to tell you the truth.
That is an edge case.
Operations is entirely edge cases. That's why I argue for hybrid strategies. Use feedback for the safety net. Only use feed forward for disturbances you are 100% sure of.
You want to interrupt the causal chain. I'm worried you're going to interrupt a perfectly healthy process.
But relying only on feedback is driving by looking in the rearview mirror. You mentioned soft sensors earlier, using things like Raman spectroscopy or off-gas analysis to calculate values we can't measure directly. You dismiss them as guessing, but without them we're flowing blind between daily samples. If we use a soft sensor to track glucose in real time, we can keep the cells in a perfect steady state. A soft sensor is a proxy. It's a correlation. And correlations drift. If your raw material vendor changes and the background fluorescence of your media shifts, your Raman model might say glucose is low when it's actually high. Suddenly, your AI controller dumps hundreds of liters of feed into the tank because of a baseline shift. A standard dumb pH probe or DO probe doesn't get confused by fluorescence. Simplicity has a quality of its own.
We aren't arguing for the removal of safety nets. The lesson emphasizes that robust control is layered. You have the PID loop at the bottom, the supervisory feed-forward on top, and the human operator overseeing it all. But to ignore the predictive capability is just to accept waste. But look, this control strategy doesn't exist in a vacuum. It lives within the life cycle.
Right. The famous stages 1, 2, and 3.
Exactly. Stage 1 is process design. Stage 2 is qualification. Stage 3 is continued process verification, or CPV. I view the life cycle as an evolutionary tool. The design space we create in Stage 1 shouldn't be a prison. Under ICH-Q12 principles, it should be flexible. Stage 3 allows us to use data to continuously refine that space.
In a perfect world, yes. But let's look at the valley of death, that transition from Stage 1 to Stage 2. This is where companies fail. You do your design of experiments in a little 2-liter glass bioreactor. You find a great design space. Then you move to Stage 2, the 2,000-liter steel tank, and suddenly nothing works. The hydrodynamics are different. The heat transfer is different. Your design space was an illusion of scale.
That's a failure of the scaled-down model, not the concept of QbD itself.
But it's a systemic failure. And then, if you survive that, you get to Stage 3, commercial manufacturing. The advocate loves to talk about learning from data, but in reality, Stage 3 is often just noise. There is a concept in quality control called tampering. It's when you treat normal, background noise, what we call common cause variability, as if it were a specific problem or a special cause. If you have a hypersensitive monitoring system, you see blips every day. If you react to every single blip, you end up tweaking a process that was actually under control. You drive it out of control by trying to fix it.
That is precisely why we need knowledge management systems. The lesson states clearly, knowledge management is the repository of understanding. We distinguish noise from signal by aggregating data over time. If we treat the regulatory dossier as a static artifact, we never learn to tell the difference between a blip and a crash. We need to let the model evolve.
I'm all for learning. I'm just terrified of the learning curve happening while we are manufacturing medicine for patients.
Well, if we want to talk about the ultimate expression of control and learning, we have to address the elephant in the room: continuous bioprocessing.
I knew we were going there, the factory of the future.
It is the logical conclusion of this philosophy. Perfusion cultures, continuous purification. Instead of struggling to reproduce a batch curve over and over, you aim for a steady state. You keep the cells in a constant optimal metabolic zone. Theoretically, this gives you higher productivity and incredibly consistent product quality.
Theoretically is doing a lot of heavy lifting there. Let's talk about the physics. Let's talk about residence time distribution, or RTD. This is the absolute nightmare of continuous processing.
RTD describes how long material spends in the process. We can characterize this.
You can characterize it, but you can't eliminate the physics of it. In a batch tank, every molecule has the same history. They all went in at time 0, they all come out at the end. In a continuous flow tank, you have backmixing. Imagine a river with eddies. Some water rushes through instantly, some water gets stuck in a whirlpool for days. That's your bioreactor. Some of your product exits too fast. It's underprocessed. Maybe the viral inactivation step didn't finish. Some product stays too long. It gets overexposed to enzymes and degrades.
But we can model this. We use tracer studies. We use computational fluid dynamics. We can define the design space to ensure the age of the product is always within safe limits.
Defining it and controlling it are two very different things. And this creates a traceability nightmare. What is a batch in a continuous stream? If you have a contamination event on Tuesday at noon, how much product do you throw away? The stuff from Monday? The stuff from Wednesday? The backmixing means the contamination is smeared across the timeline.
It requires a different mindset, certainly. You define a batch by time or volume segments. But consider the stability argument. In batch processing, the environment changes every single hour. In continuous, it's stable.
The environment is stable, but the biology isn't. This is the control bandwidth challenge. In a continuous run, you are operating for 30, 60, maybe 90 days. Cells drift. They mutate. This is genetic drift. The cells you had on day 1 are not the same cells you have on day 60. Can your control system handle a drift that slow? If your controller is tuned to catch fast changes, it might completely miss the slow creep of genetic adaptation until the product quality has already failed.
That is a valid challenge, and it's why we need that wider control bandwidth handling both the fast transients and the slow drifts. And frankly, the only way to do that is with AI and digital twins.
Ah, the black box.
It's not a black box if it's illuminated by data. Look at design of experiments. Traditional DOE is rigid. You plan 20 runs, you do them. AI-assisted DOE uses Bayesian optimization. It's adaptive. It looks at the first 5 results and says, hey, the interesting biology is happening in this corner, let's focus the next 5 runs there. It's like exploring a dark room with a flashlight instead of just turning on the lights in random corners.
It's efficient, I'll grant you that. But let's talk about the digital twin. You want to use a computer simulation to validate your process. You want to say to the FDA, we simulated a pump failure in the digital twin and quality was fine, so we don't need to test it physically.
Why not? Why burn $1 million of media on physical failure modes if a high-fidelity model can prove robustness? This allows us to explore what-if scenarios that are just too dangerous to run in the plant.
Because the FDA regulates drugs, not video games. How do you validate a digital twin? A model is a snapshot of your understanding at a specific moment in time. If your process shifts, say a filter membrane changes porosity slightly, the twin diverges from reality. If you rely on the twin to make safety decisions, but the twin is outdated, you are making dangerous decisions. This is the governance gap. Who updates the twin? How do we prove the twin is still sane?
The lesson addresses this directly. We need Alcoa Plus, data integrity. We need a life cycle for the model itself. It's not build it and leave it. You have to revalidate the model against new data periodically.
That sounds like a whole new department of people. We struggle to keep our pH probes calibrated, and now you want us to calibrate our neural networks? I just don't think the industry is ready for the maintenance burden of these systems.
It is a burden, yes, but the reward is a process that understands itself, a process that can predict a deviation before it happens and correct it. That is infinitely safer for the patient than a robust but blind system that lets a batch fail because it couldn't see the metabolic shift coming. We aren't choosing between human and AI. We're choosing between reactive and proactive.
I think that's a fair place to land. For me, the technology is impressive. I love the idea of hybrid models, keeping the mechanistic physics we know and using AI just to polish the edges. But the human factor and model risk cannot be ignored. QbD has to be grounded in reality, not just algorithmic optimism. If that fancy feed-forward loop fails, the system must degrade to a safe state, not crash the plane.
And I agree with the need for safety, but I maintain that QbD cannot remain a static submission dossier. It has to be a living system. Real-time release testing and dynamic control are, in my view, the only ways to handle the complexity of modern biotherapeutics. We can't inspect quality into the product. We have to control it in.
So the future is hybrid, not AI versus humans, but AI plus humans.
Precisely. The debate isn't whether to use the tools, but how much control we see to them, and crucially, how we prove they are working.
And for the listener, we invite you to look at your own facility. Are you still driving by looking in the rearview mirror? Or are you ready to take your hands off the wheel just a little bit?
Thank you for listening to The Debate.
Until next time.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.